Welcome back to Differential Calculus. In this video, I want to introduce you to higher order derivatives. The idea of higher order derivatives is very simply, what if we want to take the derivative of a function? On one hand, that is absolutely something we can do. The derivative of a function, right? If I have a function f of x, its derivative f prime of x is a function. And if it is a function, we can apply the rule that we already have established to take the derivative of a function to get the derivative of f prime of x. Before we get into the mechanics of that, though, I do want to at least briefly talk about why. Why are we doing this? What are we trying to accomplish? And to answer that question, I want to turn briefly to kinematics, the science of motion. The basic ideas of kinematics are taught at any physics course, and while physics is not technically a prerequisite to differential calculus, I have yet to meet a student taking calculus who hasn't had at least some level of physical science background. So kinematics starts with the idea of position. Then you start looking at the velocity or speed. And you define velocity as the change of position with respect to time. So if position is x of t, then velocity v of t would be the derivative of x of t, x prime of t. Right? Derivatives are the change. And if our function is a function of time, then the derivative would be the change with respect to time. After velocity, we have acceleration. Acceleration is the change in velocity with respect to time. So a of t would be v prime of t. And since v of t is itself the derivative of x of t, that would make acceleration the derivative of x of t, or the second derivative. We're going to denote the second derivative using two primes, two apostrophes after the variable. So a of t is x double prime of t. And in most physics classes, that's where you stop, but there's no reason that you can't keep going. The change in acceleration with respect to time is called the jerk. And that would be the third derivative of t, right? A prime of t, v double prime, x triple prime. The change in jerk with respect to time is called the snap. And at this point, the apostrophes start getting a little bit messy. So instead of continuing the chain of apostrophes, we'll generally put the number of them in parentheses. So we want 4 primes, and we'll just put a superscript 4 in parentheses. The fourth derivative of x with respect to time is the snap. Even though they don't show up very often in physics courses, jerk and snap definitely are things that you can experience in everyday life. If you hit the gas or brake pedal in your car too quickly, it will jerk you around. The snap of a whip is something that is sought after, right? Listening to a whip snap is something that people actually pay good money for. And then we can keep going, because not only does a whip snap, but it also often cracks. The change in snap with respect to time is called the crackle. And yes, that would be the fifth derivative of position with respect to time. And I'm not joking, the change in crackle with respect to time is indeed called the pop. I don't know if that came before or after serial. I've never had a good answer to that question, but it's there and we can talk about it. The sixth derivative of position with respect to time. I have never in my life seen an application of the fifth or sixth derivative mathematically. I've seen the second derivative all the time. Equations involving acceleration include Newton's second law of motion, F equals ma, which is kind of the foundation of physics. So that equation shows up incredibly frequently. It's a very powerful tool in the study of physics. The third derivative will show up every now and then in physical science. There are places in the study of mechanics, civil engineering, mechanical engineering, where the fourth derivative is important. I've never seen an equation that uses the fifth derivative, but we still have a name for it, so why not talk about it? All right, with that idea out of the way, let's start looking at a function. We'll start off with a relatively simple function. How about a polynomial, f of x equals 2x squared plus 3x plus 5. Taking the derivative of a polynomial is fairly simple at this point. F prime of x is going to be 4x plus 3. Then to find the second derivative, f double prime of x, well, the derivative of 4x plus 3 is 4. If we want to keep going, the third derivative here, the derivative of a constant is just 0. And if we keep going, the fourth derivative will be 0, the fifth derivative will be 0, and so on. Polynomials are very nicely behaved in derivatives, because if you take enough derivatives, eventually you just get the 0 function and it stays the 0 function forever. It does not have to happen that way. If I instead look at a trigonometric function, how about f of x equals the sine of 2x? Well, the derivative of sine is cosine, and then using the chain rule, we'll multiply by 2. F prime of x is 2 times the cosine of 2x. The second derivative here, f double prime of x, well, the derivative of cosine is negative of sine, then we'll use the chain rule and multiply by 2. So we get negative 4 times the sine of 2x. And we've more or less ended up where we started, right? We started with sine, we take two derivatives, we get back to sine, except there's this extra coefficient in front. And that extra coefficient is going to continue to get messier and messier. F triple prime, the third derivative, would be the derivative of negative 4 sine 2x, which will be negative 8 cosine 2x. The fourth derivative will be, well, derivative of cosine is negative sine. The negatives will cancel out. We get positive 16 sine of 2x. And it will just keep going. And the power in front will keep getting bigger and bigger and bigger. The other thing that I want to mention in this video about higher order derivatives is the notation. The first derivative, f prime of x, we sometimes note with the differential operator, d dx, acting on f of x, and sometimes we'll write that even as df dx. The second derivative would then be d dx of f prime of x. But substituting in, this is d dx of d dx of f of x. And being a little bit cute about the fact that these things kind of look like fractions, even though technically they are not fractions, we can combine that together and get d squared over dx squared of f of x, or again, d squared f over dx squared if you want the condensed notation. And that continues. If I want to denote the third derivative, it would be d cubed f over dx cubed. Very often students get confused. Why is the cube on the d in the numerator and on the x in the denominator? The reason is thinking about it as an operator. It's d over dx squared acting on f of x. For anyone who's going to continue to eventually take a course in multivariate calculus, things can get very interesting at this point when we can take the derivative with respect to several different variables. And at that point, the notation gets quite a bit messier. But for our purposes right now, I think that's far enough in that direction. I do want to wrap up by reminding you that even though this notation exists, there is no direct way of finding the second derivative of some expression. Let's look at something kind of messy. How about x times tan x? This is going to be really messy, but that's kind of the point. You can't take the second derivative straight away. You can take the first derivative. I probably would never write this step out on my own, but I think it's worth it for this first example just to more explicitly show you what I am doing. If I want to take the second derivative of x times tangent of x, that means I have to take the derivative of x times tangent of x. The derivative of x times tangent of x in and of itself is not exactly straightforward. We're going to have to use the product rule here. The derivative of x is 1, multiply that by tangent of x, plus x times the derivative of tangent, which is secant squared x. And you thought things were getting bad with the product rule with one derivative. Now I take the derivative of this. I can use linearity to separately take the derivative of tangent. Again, I probably wouldn't write this step out if I was working on my own, but I think that as a classroom example, as a board example, it's worth writing the extra step out to make sure that everyone knows where all of this stuff is coming from. The derivative of tangent is, of course, secant squared. We've already used that. To take the derivative of x times secant squared x, we're going to have to use the product rule. Derivative of x is 1 multiplied by secant squared x plus x times the derivative of secant squared. Right? That is a chain rule. We have secant and we have the squaring function. So the derivative of the squaring function will be 2 times secant x, and then we'll multiply by the derivative of secant x, which is secant x tangent x. Then do a little bit of algebra to clean this up. It looks like we have 2 secant squared x plus 2x secant squared x tangent x. Nice, simple, straightforward expression or something. Let's end with one for you to try on your own. I'd like you to find the second derivative of the rational expression x over x minus 1. Take a few minutes, see what you can do with that, and I'll see you in the next video.